Hello, and welcome to another lecture in this course. Today we'll be talking about linear equations and the integrating factor, the way to solve them. And this is section 1.4 in this book, and you can get this book at this URL. And you can download a PDF or get a cheap paperback, and that's actually the best way to support this project. All right, so let's get to linear equations. What are linear equations? So linear equations are equations, well, first order linear equations, these are equations of this form, right? So these are the equations that we'll be interested in this lecture. Now, the linear refers to being linear in y and y prime. So y prime and y only appear as first powers. They're not in some other, it's not like sine of y or something. They only appear as first power. They're not inside other functions. They can be multiplied by some function of x or some constant, but not by themselves. So y squared is not allowed. Y times y prime is not allowed. Now, the dependence on x can be more complicated. So here the f and the p, they can really be sort of any function whatsoever. And I suppose normally there could be a function of x in front of the y prime, but we could just divide by that. So we'll write them as this. All right. So linear equations are actually quite well behaved. They're quite nice. They're also easy to solve. Well, that's that's very useful for us. We'll learn how to solve them today. And fortunately, they're also quite common, right? So that doesn't always happen. A lot of times, things that are easy to solve are don't appear in the real world. So here, these appear quite a lot and are easy to solve. Now, the way to solve an equation like this is to think of this is actually kind of a interesting trick. It's not something that you would immediately probably think of. You look at this y prime times px of y, times y, and you think, well, that sort of looks like something I could have gotten from product rule, except something's missing. And so, well, what if I multiply by something? Let's call it r of x, and let's, then maybe it's something that came out of a product rule. And actually, the way that we're going to be looking at it is, well, suppose that it's actually, the derivative of r of x times y, right? Well, we have to find such an r, right? But let's suppose for a moment that we had such an r. We could find such an r. So if we can find such a function r of x, and if we can multiply everything by r, right, and rewrite the left-hand side like this, our equation just becomes this guy, right? It's the derivative of r times x, r of x times y, sorry, equals r of x times f of x, right? And then we can just integrate. We integrate both sides of this equation, right? And that gives us that r times y is equal to the integral of r times f, and then we just divide by r to solve, right? Yeah, and there is our y, right? There is our solution. The r, this function r, that's the integrating factor, right? That's the thing that we multiply by to get something that we can integrate. That's why it's called the integrating factor. Now, you'd say, well, that's all great and all, but what's r? Right? So far, well, if we have such an r, that's great, and this works, but what's r? Well, so what do we want r to be? We want an r such that when we differentiate r, we get back r times p, right? Well, that's not bad. We know a function whose derivative is itself, and we use the chain rule for our for our advantage. So we take any antiderivative of p, and we take the exponential of it. Now, the derivative of that will be just, well, the exponential of the antiderivative of p, and then the derivative of the antiderivative of p, which is p, right? So, all right. So let's try it. So let's start with this equation. Let's multiply by this r, right? So you multiply every term by this. And then, yeah, we do notice that if we take the derivative of this, right, by product rule, right, you have to, once you're going to get y prime and just this r, and once you're going to differentiate this r, and you're going to get this e to the antiderivative of p times p, and then times y, right? So, yeah, that works. And then the right-hand side, well, I haven't done anything here. So we anti-differentiate, we get this formula over here, and now we just solve for y. We're dividing by an exponential, so that's just multiplying by the exponential was a negative inside, right? Just that's the law of exponentials. All right. So let's do. Okay, maybe let's. Before we do an example, let's say, well, here is an explicit formula for this solution, right? So you could just, technically, remember this formula and just, plug it in. Let's use it, right? So let's suppose that we have this equation over here with this initial condition. And let's try to solve. Let's try to find y that satisfies both of these things. Right. So here, let's identify the different things. So p, that was the thing in front of the y, right? That was the coefficient in front of the y. So that's 2x, right? And then f was the guy on the right-hand side, and that's e to the x minus x squared. All right. So the integrating factor is the exponential to e to the some antiderivative of p. P is 2x. Some antiderivative is x squared, right? So e to the x squared, right? All right. So we multiply by e to the x squared. Multiply this thing on both sides by e to the x squared. So that's just what this is. Now we notice that it really is the derivative of this product, and over here this simplifies, right? And that's actually kind of nice. The e to the x minus x squared times e to the x squared, just by laws of exponents, right, just becomes e to the x, right? So now we anti-differentiate, and that's convenient. The antiderivative of e to the x is e to the x, right? So if we anti-differentiate, we get this guy over here, and we solve for y, right? That's basically multiplying by e to the minus x squared, and we get this general solution to our equation, right? So now we solve for the initial condition, right? So we plug in. The initial condition was when x is 0. So you plug in 0, it's supposed to be minus 1. So minus 1 is supposed to be, well, when you plug in 0 for x here, you just get 1 plus c, right? So solve for c has to be minus 2, right? Okay, so c is minus 2, so that's our solution, right? So maybe something that I didn't quite say, I said that when we came up with the solution, it wasn't just some solution. It was actually the general solution. You will always be able to solve for the initial condition. So it has that c in there coming from the integration, right? When you integrate, you get the c, and then you solve for the c and get your a particular solution solving your initial condition. Now, couple of remarks. So first, you can really pick any antiderivative of p. You don't need to put in the constant of integration there. You need to, for the second integration, when you actually integrate the equation, that's where you do need to put in the constant of integration. That's the one that will solve the problem for any initial condition. But when you're doing the integrating factor, any antiderivative will work. You just need some integrating factor. You don't need the most general one, right? So any one will work. And if you actually put in a constant of integration, it will actually essentially drop out. So nothing bad happens if you put it in there. It's just you waste some ink on the paper when you're writing it. Or if you compute the antiderivative differently, it doesn't matter. Just any antiderivative. Now, I usually, I wouldn't be able to easily remember the whole formula. I mean, it's kind of nasty. But the idea is really simple, right? So if you remember the idea that you have to multiply by something, and so that the left-hand side becomes essentially a product rule, and then, it might be good to remember that R is the exponential of the antiderivative of p. Right? That's easy to remember, and then you just work through, right? Just like we did over here. I didn't actually just plug it in directly into the formula. I worked through it, right? I multiply by the integrating factor, and and integrate it, solved, right? I mean, I work through the process instead of just plugging into the equation. That's the way I find it much easier to remember, right? I don't have to remember that complicated formula. I can just remember. I mean, the procedure is simple, and it's all these rules that you have to remember anyway, right? All right, now the formula, right? I mean, if you write it all down, there's a bunch of integrals there. Bunch of indefinite integrals, and you can't always find them in closed form, right? So sometimes you can just you can get a solution in terms of definite integrals, and there's nothing wrong with writing things down as definite integrals. If you have to have a computer approximate definite integrals, it's very very quick to do that. There's no issue with computing integrals. So you can write down the definite integral version of this as well. So consider a linear equation with an initial condition, right? We can actually give an explicit formula for a solution that satisfies this equation, right? We just write it out, right? You write out the antiderivatives as definite integrals, right? And you start, you always have to decide where do you start the integration. Let's just start it at the x naught, right? That's a convenient one, right? And then we'll do for the p, right? Let me undo some of these highlights. For the p's, right? We'll do this integral just from x naught to x. Now, you have to notice that there's all these dummy variables in there, right? Because you can't just put x's in everywhere, because that would get confusing, right? I mean, over here you're integrating with respect to t, so there should be t somewhere, right? The t is in here and the t is in here, but the dummy variable in the integral for p, right, has to be something else. So I've made it s, right? But essentially, you just write it out. And you could just write down c in here, but you'll notice that y naught will work, right? Because if I plug in x naught, right, all of the integrals, but namely these two, right? Over here, if I plug in x naught for x, right, this just becomes 0, so it's e to the 0. That's just 1. This integral just disappears, right? It's 0, right? So I will get, when I plug in x equals x naught, I just get this constant here. Yeah, so it works, right? Now, you can do an exercise with this. Write down the solution for this guy, right? As a definite integral, you cannot do it as a, there's no closed form solution, but you can write it as a definite integral, right? Basically, just plug it into this formula, right? Now, this formula actually gives a stronger version for Picard's theorem, which is the existence and uniqueness of solutions of differential equations, of ODEs, ordinary differential equations, for linear equations, right? Because what it says is that you don't just get solutions for a little bit. Because you have a formula, you get solutions whenever the f and a p and the p are continuous functions. So on whatever interval this thing makes sense, the solution is going to make sense. So that's a stronger conclusion from Picard, right? Basically, there's nothing like, if you remember y prime equals y squared, right? The solution didn't always exist for all time. And depending on your initial condition, it blew up at different points, right? Always existed for some interval of x's, but you would have to actually solve this to figure out when does it blow up, right? For linear equations, for equations like this, because you have a formula like this, you don't have to worry about this thing blowing up. All right. I mean, unless P or F blow up, right? Basically. All right. So let's look at sort of a typical example of using linear equations, right? So suppose that we have this 100-liter tank, right? And let's suppose at first it contains 10 kilograms of salt and 60 liters of water, and it's dissolved, and it's really well stirred, right? So everything is perfectly dissolved always, right? So we're simplifying that, right? It's not going to have different concentration in different places. Everything is uniform concentration everywhere. Now, there's some brine flowing in, right? There's stuff flowing in at 5 liters per minute, and this has concentration 0.1 kilograms per liter. So in every liter, there's 0.1 kilograms of salt, right? And it's flowing in at 5 liters per minute. Now, we also have this spout on the bottom, and it's flowing out at 3 liters per minute. Right, so we're draining at 3 liters per minute, right? That's draining the stuff that's inside, right? Okay. So a question, one of many questions we could ask, but maybe we could ask how much salt is in the tank when the tank is full, right? All right. So let x be the number of kilograms of salt in the tank, right? So that changes, right? That's really the thing that we're interested in. And let t be the time in minutes, right? Because everything's given in minutes, so let's use those units. All right. Now, for a small change in time, and we're going to call it delta t, how x changes, right? We're going to call it delta x, is approximately as, well, there's salt coming in. How much salt is coming in? Well, we have the rate in, that's 5 liters per minute. That's how much brine is coming in. That's in liters per minute. We need kilograms of salt, right? So I multiply by the concentration that's coming in, right? So it's liters per minute times kilograms per liter is going to give us kilograms per minute. So if I want to know how much X changed, I need to multiply that by the time, right? The little bit of time that I'm looking at. So that's delta T, right? So that's how much salt is coming in. Now, how much salt is coming out? It's the same thing, right? All right, but now it's the rate out, concentration out, right? Now you divide by delta T, right? So divide by this guy, you're gonna get delta X over delta T over here, and then you let delta T go to 0, so you're gonna get the derivative of X with respect to T, right? So the derivative of X with respect to T is the rate in times concentration in minus the rate out times concentration out, right? So okay, so that's the sort of general formula for this sort of problem, and we plug in what we're given, right? So rate in is 5, right? Concentration in is 0.1. Rate out is 3, and concentration out, well, this is the complicated one. Well, it's the amount of salt inside divided by the volume, right? The amount of salt is X, so that's easy, right? What's volume? Well, the volume changes, right? If you think about it, well, we're starting at 60, and it's changing. Well, 5 is coming in, 3 is coming out, right? So it's 5t minus 3t, so 5 minus 3t, right? So 60 plus 5 minus 3t is the volume, right? Okay, so we just write down what the equation is. That's what it is, right? Or if we simplify it a little bit and put it into the form as a linear equation, yeah, that's what it is, right? We have the derivative, and then we have our p over here times the dependent variable, right? And then we have our f, which is the right-hand side, that's 0.5 here, right? All right. So let's solve this guy. So here the integrating factor is, well, we take the p, right? And notice how like the variable names didn't matter, right? So we have the variable names are different, right? That's normal, right? So we have X is now the dependent variable, right? And T is the independent variable, right? That's why we're integrating with respect to T here. All right. So this is our P. We find some antiderivative and we take the exponential. Well, so you do a little bit of calculus. You find that the antiderivative is this. You take the exponential. Just using the laws of logarithms, this 3/2 goes upstairs, and then the exponential logarithm will cancel out essentially, right? Kill each other. Because the exponential is the inverse of the log. The log is the inverse of the exponential. So you have what r is. It's 60 plus 2t to the 3/2 power, right? So we multiply our equation by that, right? We make the left-hand side be the derivative of a product, right? We integrate, right? So the left-hand side is still this. The right-hand side is now this. And we solve for x, right? So we divide by this guy, right? So it's just like multiplying by the minus 3/2 power, right? And so we get this formula over here. And we we can compute this. This is, just a little bit of calculus. So, if you compute this integral, you get this guy over here, right? Or the definite integral, antiderivative, right? And we simplify a little bit this -3/2. When you add it to 5/2, it just becomes 1, right? So we just have the first power here. That's the over 10, right? And this thing didn't change, right? So this is, this is the solution, right? The general solution, right? Okay, so we had the general solution. We now have to find a specific solution. So in the beginning, there was 10 kilograms of salt, right? So x is 10, t is 0, right? So x at 0 is 10, and you just plug it into the formula, that we got that says, and you solve for c. So you'll simplify, right, and solve for c, right? So c is going to be this guy over here, right? Yeah, just a little bit of algebra, right? Arithmetic, really. All right. So here's the graph. So here's the graph of the solution, right? So it started at 10, and then it's growing, right? There's actually more and more salt in the tank. So when is the tank full? So the tank is full when, this was the volume, 60 plus 2t, when that equals 100, right? So that happens when t is 20, right? So what is x when the tank is full? Well, it's going to be this thing. Well, was this c in there, right? So we're going to plug in that c, right? This guy, I'm going to plug in over here. That's approximate, right? And we get approximately 11.86 kilograms of salt when the tank is full, right? And the concentration, well, that's just you divide by 100, which is the volume when the tank is full, right? You get approximately 0.1186 kilograms per liter, and you can note that we started with 0.167 kilograms per liter. All right, so that's a typical typical application. We're really interested in this number, right? How many kilograms? That was the question, right? This is a fairly typical application of linear equations. Sort of a typical homework question, for example, right? All right, so that's it for this lecture. So see you next time.